Good day, ma'am. I am Jubilin Unto, BSEd Science 2B. I'm the third reporter of Chapter 29 with the topic of Application Involving Charged Particle Moving in a Magnetic Field.
We have here figure 29 to 11. So, as you can see, we have here the path of particles. The magnetic force exerted on the particles near either end of the bottle has a component that causes the particle to spiral back toward the center. So, in this figure, we know the process of positive charged particles moving in a non-uniform magnetic field, or that's what we call a magnetic bottle, because charged particles can be trapped within it. So the magnetic bottle has been used to confine a plasma, a gas consisting of ion and electrons. Such a plasma confinement scheme could fulfill a crucial role in the control of nuclear fusion, so a process that could supply us in the future with an almost endless source of energy. So, unfortunately, the magnetic bottle has its problem. So, if a large number of particles are trapped, so it might be the collision between them cause the particles eventually leak from the system. So that is the process of the path of particles. In addition, it acts as magnetic mirrors because charged particles reverse their direction of motion when approaching one of the poles. So, as a result, the trapped particles bounce back and forth in the field. So, that is the process on how the positive move in the magnetic bottle. In this figure, the Van Allen radiation belt consists of charged particles, mostly electron and proton, surrounding the Earth in donut-shaped regions. In figure 29 to 12, the particles trapped by the Earth's non-uniform magnetic field. So, the spiral around the field line from the pole to pole, covering the distance in only a few seconds. So, these particles originated mainly from the sun, but some come from the stars and heavenly body objects. For this reason, the particles are called cosmic rays. Most cosmic rays are deflected by the Earth's magnetic field and never reach the atmosphere, so some of the particles became trapped. However, it is these particles that make up the Van Allen belts. So when the particles are located over the poles, they sometimes collide with atom in the atmosphere, causing the atoms to emit visible light. Such collision are the origin of the beautiful aurora borealis or northern lights in the northern hemisphere and the aurora australis in the southern hemisphere. Aurora are usually confined to the polar region because the Van Allen's belts are nearest the Earth's surface there. Occasionally, though, solar activity causes larger number of charged particles to enter the belts and significantly distort the normal magnetic field lines associated with the Earth. So, in this situation, an aurora can sometimes be seen in the lower latitude. Example, the magnitude of the magnetic field throughout our galaxy is an order of 10 to the power of negative 10 t. So, charged particles move in very large circle due to the magnetic force on them. In this figure 29 to 13, a velocity selector when a positive charged particle is moving with velocity v in the presence of the magnetic field directed into the page and an electric field directly to the right. So, it experiences an electric force QE to the right and a magnetic force QV times B to the left. in velocity selector in one experiment involving moving charged particles. It is important that all particles move with essential the same velocity, which can achieve by applying a combination of an electric field and a magnetic field oriented as shown in figure. So, a uniform electric field is directed to the right in the plane of the and a uniform magnetic field is applied in the direction perpendicular to the electric field. Q is a positive and the velocity is upward. The magnetic force QV times B is to the left and the electric force QE is to the right. So, when the magnitude of the two fields are chosen so that QE is equals QVB, the forces cancel. The charged particle is modeled as a particle in equilibrium and moves in a straight vertical line through the region of the fields. From the expression QE is equals QVB. This formula only those particles have the speed pass undeflected through the manually perpendicular electric and magnetic fields. The magnetic force exerted on particles moving at speed greater than that stronger than the electric force, and the particles are deflected to the left. Those moving at slower speed are deflected to the right. In this figure, a mass spectrometer positively charged particles are sent first through a velocity selector and then into a region where the magnetic field B causes the particles to move in a semicircular path and strike a detector array 2P. A mass spectrometer separates ions according to their mass to charge ratio. In one version of this device, known as the Bainbridge mass spectrometer, a beam of ion first passes through a velocity selector and then enters a second uniform magnetic field to be with 0 degree that has same direction as the magnetic field in the selector. Upon entering the second magnetic field, the ions are described by particle in uniform circular motion model. They move in a semicircle of radius r before striking a detector array at P. If the ions are positively charged, the beam deflects to the left as figure shown. If the ions are negative charged, the beam deflects to the right. From equation 29 to 3, we can express the ratio M over Q as electrons are accelerated from the cathode, pass through two slits, and are deflected by both an electric field formed by the charge deflection plates, a magnetic field directed perpendicular to the electric field. The beam of electrons then strike a fluorescent screen. The cyclotron is not only the type of particles accelerator. The cyclotron is important historically because it was the first particle accelerator to produce particles with very high speed. Cyclotrons still play important roles in the medical application and some research activities. Many other research activities make use of a different type of accelerator called a synchrotron.